I think that we are going to be able to complete the lecture on hard operational research tomorrow, probably, and then we shall be issuing you we shall be posting the term project that you have to carry out with your groups. We shall also post some guidelines about how to proceed with the term project. And also, if I can find the time, I will write some, maybe 1 or 2 pages of guidelines of how to write reports for such projects, okay? So let's make an effort and try to finish this today. We have talked about modeling, and we indicated that models should be tested. Now, testing the models is of 2 types. You test the internal validity of the models, and also there is the external validity. Validity means that your model is going to be useful. Internal validity means that it is internally consistent and correct. This is usually mathematical correctness in the case of mathematical models. External validity is about whether your model is capable of representing the real world, the reality. These concepts of validity and also an associated concept of reliability are fundamental not only to mathematical modeling or operational research, but generally in science. Therefore, in this part of the lecture, we are trying to make sure that we understand these concepts properly. Now, going back to validity, in science, in research, validity is about, well, most of science and research in the empirical leg of research, let's say, is about making measurements. You make measurements. You have, in research or in science, you have theory and you have experiments and observations. Using your knowledge of theory, you propose hypotheses which you then test using experimentation if possible, and observations only if experimentation is not possible. Obviously, observations and experimentation always involve measurement. So validity and reliability are closely associated to the problem of measurement. Validity means that if your research is valid, it means that you are measuring what you have in mind to measure and not erroneously measuring something else, okay? And this can be understood mathematically by looking at an association. Therefore, as you can see here, the variable y can be written as a function of several other variables, x, w, z, etc. We don't know how many variables there are here. There may be many, many. The reason that we do not know how many independent variables influence the dependent variable y is complexity. If you remember the butterfly effect, it's as if everything affects everything else in the universe. So we do not really know how many independent variables there are. Suppose that we are interested in the effect of the variable x on y. That is, we would like to see that if we change x by delta x, the change we observe in y, which is represented by delta y, will be the result of only delta x, and not the changes in other variables like w, z, etc., not delta w, delta z, etc. Okay, this is fundamental in research. So this is what we would like to have. Delta y, we would like to make sure that delta y is equal to f of x plus delta x, w, z, etc. are remaining constant, minus f of x, w, z. These are the original values of the variables. Only one of the original variables, x, is allowed to change by delta x, okay? So we would like to make sure that this last expression holds in research. Now, how can we do that? We have discussed this in other contexts. So actually, we are returning to a discussion we had earlier. Validity would be assured if we could exercise complete control over measurement. Control, the concept control, we have introduced this before. Control means that all the other possible causes are kept unchanged. That is, we have to make sure that delta W, delta Z, etc., must be equal to 0 when we are taking the measurement. Now, making sure that all the other variables remain constant can be possible if it is possible. The medium in which this is possible is called a laboratory. A laboratory is a place where we can keep all the variables that we are not interested in at constant levels. But normally, especially in the social sciences, in economics, in operational research, etc., usually there is no laboratory. As we know, open systems cannot be brought into a laboratory. So what we can do is to apply a stimulus delta X. This change is applied. A stimulus is something which moves something else, okay? So delta X is applied so that it will also force Y to change by delta Y. A stimulus delta X is applied to a group we call the experimental group. And the stimulus delta X equal to 0, that is no stimulus, is applied to a control group. So we form the experimental and the control groups. You remember that we discussed this in the context of the Hawthorne effect, in the Hawthorne effect, in the Hawthorne research. These two groups are selected randomly from a population, so these are random samples. Now, the significance of samples being random should be obvious to you. It means that if a sample is selected randomly, then the sample can be representative of the population. If, for example, in this class of, let's say, 90 students, we select a random sample of 10 students randomly, concerning many moments, the averages or means, etc., this sample will represent the population. Their moments will be approximately equal. The first requirement is that the samples must be random. The second requirement is what? What's the second requirement if you are sampling? What would you be interested in? Size, right? Sample size. Of course, the sample size should not be too small. I mean, if we select one person, probably he or she won't represent the entire population, etc. So random samples are important, or that we have random samples is important. So when we do this, we have an experimental and a control group. Since we are not in a laboratory, we cannot stop WZ from changing. Delta W is not 0. Delta Z is not 0. These could only be 0 in a laboratory. Outside a laboratory, we cannot control them. So the idea in having two groups, the experimental and the control groups, is that the effect of changes in WZ, etc., will cancel out. How will it cancel out? Well, we will look at the change in Y for the experimental group and also for the control group. So you look at the difference between the changes in Y in the experimental and the control groups. You see, this is the change in Y in the experimental group. In the experimental group, what we are doing is all the variables are changing, but the X variable is changed by ourselves. Or rather, we know how X is changing. In the control group, everything else is changing except X. We stop X from changing for the control group. And then when you take this difference, when you subtract delta YC from delta YE, you will see that these will cancel out. The constant terms will cancel out, and we shall be left with the difference of the, I'm sorry, I pushed the wrong button. Okay, so if you, I didn't write it again, but if you take the difference of the first line from the second, of the second line from the first line, you will see that you will have only the differences between the first two terms, which represents, therefore, the effect of x only on the, by taking the differentials between the control and the experimental groups. Since the two groups are members of the same population, those second terms will cancel out. Okay, so this is the idea of an experiment. If an experiment outside the laboratory is capable of providing this sort of design, in which we have two representative samples from the same population, called the experimental and the control groups, and the stimulus X is applied only to the experimental group, and the difference in the effects is calculated as such, then if delta Y is greater than 0, when delta X is greater than 0, we shall know that the change in X has an influence on Y, okay? If delta Y is equal to 0, if there is no change, of course, then the changes in X are not affecting Y. So we will know that X is not an important determinant of Y. So this is the idea. If we are able to establish this relationship and see that delta Y is producing delta Y is a result of a change in X in delta X, then we say that the relationship between X and Y is non-spurious. Non-spurious. These are technical terms that I would like you to be familiar with. A non-spurious relationship is a true relationship, not a false relationship. You are familiar probably with spurious relationships. There is a story, for example, that I used to tell when I was teaching similar courses before. In the United States, for example, when automobiles were not yet invented, people used horses for transportation. And thieves, of course, stole these horses from one another, from the owners. So thefts, atırsızlığı, was a very serious problem in the United States. And the police force or the sheriff or whatever were always looking for horse thieves. And then when statistics was invented in England first and then came to America, people started using statistics to see why horse thefts were increasing, for example. What was the other variables which resulted in an increase in the number of horses stolen? And the joke was that as the number of priests, the church clergy, priests were seen to increase in the United States, also the horse thefts were also increasing. Now, this sort of relationship is not very meaningful, obviously. These clergymen would not be stealing the horses. This sort of relationship is called a spurious relationship. It means that there is a true variable which we do not observe at the moment that affects both the number of the clergy and the number of the horses stolen. What do you think that other variable is? Population, obviously. As the population of the United States increased, both the number of horses stolen was increasing and the number of priests in the churches was also increasing. So this is a very simple mistake, but this is very, very important, this mistake, not falling into the trap of making this mistake is extremely important in science. Otherwise, you will end up with what we call not a true relationship, but a spurious relationship. Okay, so non-spuriousness is important. Experiments conducted with control groups are said to have strong designs. We say that this experiment has a strong design so that we can rely on the results. And in this way, internal validity is assured. Hence, the controlled experiment is the most powerful research instrument in science. If scientific disciplines are capable of conducting such experiments with strong designs, then usually these disciplines are the most advanced. That is why laboratory sciences are probably more advanced than other sciences, and also social sciences in which you can have control groups are more advanced. Experimental designs will be weaker if there is no control group. In some disciplines, experimentation is not possible with or without control groups, and such disciplines have to rely on much weaker designs. Economics is a classical example. We can't have any experiments at all, weak or strong in economics. So the results of economics research have weak validity, have limited validity. The internal validity of models that are used in economics, in OR or industrial engineering, is restricted to logical and mathematical correctness. Usually, now we are switching from measurement to models, but the concepts are all common, okay? In models, the internal validity is, as I said, mathematical correctness, and this can be checked. We can establish whether the model, or in fact, whether the experiment has strong or weak internal validity. Now let's switch to the next component of validity, which is external. This is also called generalizability of research findings. Suppose that we have been able to establish a non-spurious relationship between X and Y. Even when a non-spurious relationship is established between X and Y under laboratory conditions, the relation can fail to hold under real-world conditions. When we take the experiment, carry it outside the laboratory, the relation may not work, because in the laboratory, the world is frozen. Only X is allowed to change. But in the real world, everything is changing all the time. So this is what we mean by external validity. Outside the laboratory, the concern is about the representativeness of samples. Are we sure that the samples, let's say, that we have control groups, experimental groups, etc., samples may not be truly random or of sufficient size? If, therefore, we have questions about the representativeness of the samples and therefore about the generalizability of our results, then the effects which stop, which moves away the representation of the samples are known as also reactive arrangements. Hawthorne effect, for example, was a reactive arrangement. The control group and the experimental group in the Hawthorne experiments reacted to being measured. So they increased their productivity even when the lighting conditions were not improved. Such reactive arrangements also is a concern for external validity. In general, there is no definite way to ensure external validity of research designs or of mathematical models. Usually, for example, if you are a researcher and you publish articles in academic journals, there is a refereeing process. The referees look at your article, make corrections or ask you to make corrections on it, and when they are satisfied, your article is published in an academic journal. What they are checking is internal validity. Usually they are not able to check external validity. It's too difficult. I mean, they, of course, try to make attempts to establish external validity also, but it is usually very, very difficult. Hence, generalizing research findings to real-world situations is always problematic and requires caution if you do not want to end up in bullshit. Huh? Bullshit is also an academic term. Yes. I mean, if you look up bullshit from the Google, write bullshit and Frankfurt, okay? Frankfurt and bullshit, and you will get very interesting results and videos. I advise you to watch that video. It was recorded of Professor Frankfurt in Yale University about bullshit. I have also written some notes about bullshit. Maybe I'll send them to you in Turkish. Okay, reliability is another key attribute of research design and of measurement. So let's spend just a little more time on this. This is about stability or about the absence of random errors in measurement. I gave you the example last week of trying to measure the distance from this desk to the wall, for example, using a meter stick. Usually, the results of such a measurement will be valid, and also they will be reliable. We know what validity is. The distance, if it comes out as 6 meters, for example, and I repeat the measurement several times, at each time the result is the same. So I know that the measurement is valid and reliable. But suppose I make the measurement not with a meter stick, but by an electronic gadget like this. Okay? I make the measurement 10 times, and 10 times the result comes out as 1 meter. Now clearly, this measurement is not valid because the distance is greater than 1 meter. But in each of the 10 measurements, the result was 1 meter. So my measurement is reliable. But it's not valid. Do you understand? Okay? So reliability is about random errors. If I make the measurement again with this, and the answer comes out 6.5 meters, 7 meters, 6 meters, 5.5 meters, etc., probably the instrument is pretty valid, but the measurement is not reliable. Okay, so the idea of validity and reliability are very fundamental. A reliable measurement may not be valid, for example, if it turns out that the distance comes out as 1 meter each time. The reliability of mathematical models is usually not a problem, since a model will produce exactly the same output when the same input data set is used. If it's an LP model and you feed the same data set, an LP model is measuring something. So the concept of measurement is extremely important in science. All science relies on measurement. I don't know if they teach you measurement in any of our courses. Anyway, so a model is a measuring instrument. It's like a calculator, I told you before. It measures something. And obviously, if you use the same input to an LP model, always you will get the same results. So reliability is not a concern for us. However, we should know how sensitive model results are to input data. Now, this concept carries over to something else, which is pretty important for us. We would like to know how sensitive our model is to input data. It's an important step in hardware and helps to question the robustness of a model, model robustness and vulnerability to errors. If, for example, your model is producing a result which does not change easily as you change the input data, like a robust solution in which, for example, the same basic feasible solution in an LP model comes out as optimal, even though you make changes in the data. So that's the concept of robustness. And of course, the external validity of the model comes also into question here. How does this come into the picture? the external validity? Well, it's about the data that you use. The data that you use is like a sample you get from a population. If the data you use is not representative of the real problem situation, obviously the results you get will be bullshit. So sensitivity analysis helps us discover or question these issues. So please make sure that you understand these. I will set several questions on these in exams later on. These are the important concepts. I mean, probably you are now aware of what this course is about. This course is about concepts and about thinking. It doesn't give you instruments that you can use like a key to open locks. It helps you to think out the keys that you will use for opening locks. So the concepts are extremely important in this course. Modeling, now remember that we are discussing the steps of the hard OR methodology. The first step was the formulation, or the first phase is the formulation phase. The second phase was modeling. The third phase was implementation, right? Now we are discussing modeling, and as we were discussing modeling, we diverted into the questions of validity and reliability, which are relevant for modeling. Now we go on from there. Let's assume that modeling is completed. We have tested it for internal and external validity as best as we can. It should end with the submission of a project report, complete with findings, recommendations, an account of the strong and weak parts of the inquiry, and all supporting evidence that is necessary. So a project report is written, is prepared, and submitted to whatever authorities. The authorities are the problem owners, obviously, and it should include all these things. Then comes the third phase of hard OR, is implementation. I'm not going to spend too much time on this. It is usually necessary to plan the implementation. Now, this is the implementation phase, of course, involves industrial engineers, but it will also involve who will be involved in the implementation? The problem? Users, the problem users. Remember users? The users are the people who will implement your recommendation. For example, the inventory manager or the production manager. The production manager need not be, he could be a mechanical engineer or whatever. So all these people would also be involved in implementation. And as an industrial engineer, you would do well to plan the implementation involving all these people beforehand, establishing control over the solution. What does this mean? That is when is it necessary to update the current solution and why? You will look out for any needs for revising or modification of your solution. Then, of course, the implementing phase will come, and after that, auditing. Auditing is like checking whether the implementation has produced the results that you intended to have in the beginning. What is being checked here? Auditing checks what? Yes. What does it check? When I ask such questions, please try to answer in terms of the technical terms that we have learned, not in general terms. Effectiveness. Effectiveness. Auditing tries to check whether the solution you have proposed have been effective. Effectiveness is about achieving long-term goals. Okay, so that's a rough summary of the hard OR methodology, and our book is very nice in that they have provided a very good case study. This is called the LOD case study. I think the author, Dallenbach, has worked a lot with oil companies in the United States before he became an academician. And this is one of the projects he worked on, or rather he produced this case from his past experience with the oil industry. LOD lubricating oil division. There's a refinery. A refinery is part of an oil company, as you know. And in this refinery, crude oil is processed and into finished products. And normally, the products of crude oil come in several classes, like fuel, like gasoline, diesel fuel, etc. But there are also lubricants, yani madeni yağlar. So the LOD is a department of the refinery which produces lubricating oils. It's a simple application of hardware that illustrates the first 7 steps of Figure 6.1. Figure 6.1 is the figure where you have these 3 phases, the formulation, modeling, and implementation. Now, this department, LOD, manufactures and sells about 400 types of lubricants in containers to over 1,000 customers, and these lubricants are made from refinery products. So they have 400 different products, which we can call SKUs, stock keeping units. For example, you can have 1 drum. These containers are drums, varil. There are small ones, large ones containing the same lubricant, but they are considered to be different products probably. Anyway, 400 different products. Now, the auditors of this company, the auditors of a company are financial auditors, people who check whether the company is profitable enough, if it is doing well, etc. The auditors can be people from inside the company, or they could be independent auditors. They report that LOD stock turnover averages 12 per year, well below the company target of 24. Now, the company, the refinery, has set a target of achieving an annual turnover of 24. So that is, the entire stock will have to be renewed 24 times during 1 year. However, in the case of the LOD, this has come out as 12, which is not satisfactory. The Vice President for Finance brings this issue to the attention of the Vice Presidents for Production. He says, look, we have this department where they are performing under our target, underperforming. Who then asks the LOD manager to deal with this issue. Then the manager of the LOD is instructed to look into this problem and bring his performance up to the level of the company requirements of 24 per year. The manager of the LOD then asks the advice from the OR department at the company headquarters, and the preliminary study is initiated. Now, this study is a scoping study. The OR people from the headquarters will conduct this case study, not as a full-scale study, because for a full-scale study, all the 400 types of lubricants have to be examined. Instead, they take a sample product and try to find out whether they will be able to achieve any improvement over the entire product range. So it's a scoping study. Now, this is a rich picture for LOD. It's a very nice, rich picture. Please don't think that making pictures is useless. This is extremely useful. And if you have a good example like this one of a rich picture, then spend some time on it. Look at it for half an hour and understand, and of course, comparing it with the text. See all the facts mentioned in the text, how they are translated into pictures, okay? So you can see that at the top over there, there is the refinery. This is the bigger company. It's called Sandpoint Refinery. They make several products. Some of them are called base oils. Base oils, baz yağlar, are the primary products which are used by LOD to produce the finished products. Actually, what they do is they take different types of base oil and mix them in certain proportions and maybe put in some additives to produce the required finished products. As you can see here, they have mixing vats. A vat is a large container for chemical processes. And they mix these base oils and they fill them into containers, the empty containers, as you can see. Some of them are tested in the testing laboratory. It turns out that 95% of the batches, the production batches, turn out to be okay. Then 5% fail and they have to be reprocessed. So you can see there are many. The full containers are put on pallets, paletler üzerine yükleniyor, and taken to the warehouse where they are stocked. 804 products. Why is it 400? I don't know. Well, 804 different products, counting all the SKUs, let's say. 400 basic products, but 804 products are produced. What else is pictured here? Well, all these are put into the Sandpoint warehouse, as you can see. They are then transported from the warehouse by trucks or by railroad to the customers. The customers are of two types, as you can see. There are the big customers, represented by the fat man, and there are the small customers. The small customers require between 800 to 1,000 containers. If the order coming is greater than 1,000 containers, then this is accounted as a big customer. Otherwise, the order is accounted as a small order. The small orders are met from stock. The big orders are met by special production run. There's a production schedule. Production lead time is 4 to 6 hours. Shortages are not allowed. You can see that the shapes that we use are completely arbitrary. There are no rules. It's very flexible. What else do we have here? Here is the vice president for finance, and this is his eye. He's looking at the situation. And what he sees is that the current stock turnover is 12 times per year, per annum. And investment is too high. The target is 24 times per year. So that's what he diagnoses. Obviously, if you are able to turn your stock only 12 times during 1 year, it means that since shortages are not possible and all orders are satisfied, then obviously you are keeping a large amount of inventory. Okay? So reducing the inventory will speed up the turnover. So that's the idea. This is a nice big picture of. Just make sure that you read this case. Again, I will make use of this in. Now, adjusting these can improve turnover. That's the idea. The current service level can also be adjusted for better turnover. Current service level means delivery is to be made in, let's say, 2 weeks or something like that, or 2 days, whatever. This is about the service quality. For example, you can bargain with the customers and maybe prolong the delivery lead time, etc. But this is not really allowed, as we shall see. The vice president for finance and the load manager share the common worldview. They say, make efficient use of LOD resources, that is, minimize costs. And the finance vice president thinks, speed up stock turnover, that is, reduce inventories, which will save from capital costs, so your turnover will increase up from 12. But the LOD manager also thinks that the setup cost must also be considered, because as you can see, if inventory levels is to be reduced, how can you reduce the inventory level? By increasing the number of batches to produce, right? You don't keep any stock, but you start a production run whenever it is necessary. It is like, in the extreme case, it is like working with zero stocks. But of course, this is not feasible because setting up, it's not a single product, and there are 804 different products. So obviously, there will be setup problems, and setups as, you know, also cost. But the current service quality should not be played with. I mean, it should be maintained. That is, the lead times, the delivery lead times should not change. So, making these observations, we are able to identify the narrow system of interest fairly easily in this case. It's the production and inventory system of the LOD department, the narrow system. The wider system is the entire LOD operation, which includes, for example, customer relationships, lead times, facility allocation, resource allocation, etc. We are going to come back to these, but let's proceed with the obvious elements. The elements of the problem, there's the decision maker, who is the LOD manager. His objective is achieving low operating cost for the LOD operation, subject to maintaining the same level of customer service without any deterioration in the customer service. He would like to minimize operating costs. The performance measure is the total operating costs of the LOD. The decision criterion is minimizing total costs. Now, what are the alternative courses of action? The first one is adjusting stock replenishment batch size. And the second one is adjusting the cutoff point separating big and small orders. As you can see, no other alternative courses of action are considered. So if you only adjust the batch size and the cutoff point, then what you are doing is you are establishing your inventory policies to minimize inventory costs. Production costs are irrelevant here. Prices are irrelevant. Only the inventory costs are targeted in this exercise. The wider system of interest is the LOD operation and the refinery itself also. The problem scoping, rather than a full formulation, was the first step. Now, this part is very, very important. What are the boundary judgments that we have already made? This is the problem of boundary setting. Now, unconsciously maybe, we have already made several boundary judgments. A good engineer and a good industrial engineer should always keep in mind that he has set these boundary judgments. He should not make them unconsciously. He should make them consciously and knowingly. So you should be able to answer questions describing a problem situation and the decisions taken to discover what boundary judgments have been made. What are the boundary judgments that we have made here? Well, the first one is that orders, the incoming orders, lie outside the wider system. We make this boundary judgment. That is, we do not bargain with the customers to manage their sizes of orders, etc., anything like that. Okay? Facilities also. We are not interested in whether we have enough capacity to implement the problem, the solution that we are about to formulate. We assume that we have the necessary manpower, we have the necessary filling or the drums or other facilities of transportation, warehousing capacity, etc., are all considered to be adequate. Normally, probably they are adequate, but don't forget that we are making this assumption. This is a boundary judgment. Sharing equipment and depot capacity by different products assumed independent at the beginning. Investing in equipment and depot capacity is not an option. Maybe if we extend our depot, maybe, I don't know, maybe if we decrease the size of our depot by decreasing the levels of inventories, we shall achieve even more savings in cost, but these options are not considered. Demand management, as I said, is not an option. These are not strictly true. I mean, these are not things that we have to make, I mean, these assumptions. We may later on relax these assumptions. When we relax the assumptions, the problem we formulate will become more complex, more complicated. But time will tell us whether it is necessary to do this. In fact, any solution produced by the LOD study is likely to affect facilities and customers, obviously. So our boundary judgment is not really truly realistic. Okay, let's look at this figure also. The high-level system structure diagram for LOD. The textbook introduces and describes different diagrams. This is one of them, system structure diagram. I don't think that we need to formalize such diagrams too much, but it's very useful. It represents the whole problem very nicely. Huh? This is much sparser than the rich picture. The rich picture is very rich. This is sparse. Sparse means seyrek, huh? not rich. But it focuses on the problem. The customer orders are coming. Here, the shapes used are the shapes of an influence diagram. The cloud over there is something which we do not control. Comes out. The customer orders come. Then we classify the orders by size. We decide whether, by looking at the cutoff point, if the orders are large, then large order subsystem meets orders by special production runs. The decision that takes us here is the cutoff point. The small order subsystem meets orders from stock. Again, the decision here is the stock size. Existing production and forklift facilities are given, and we do these, and then ship the product to the customer. Okay, let's stop here.